Okay, so let us start on our discussion on the expectation maximization algorithm. Okay, so what we did so far, we are interested to maximize over theta the likelihood of the data given the parameters. We found that this is a bit difficult to maximize. So instead, using the Jensen inequality, we lower bounded it by some quantity which we call the variational lower bound, which is a function of z values less theta. And we followed an alternating optimization. We followed, so if this is your log of px given theta, we first, for a given value of theta, let's say theta k, we find a L which gives the highest lower bound, the strictest lower bound, keeping theta fixed at theta k in the E step, and then afterwards keeping this q or the variational distribution same, keeping this q same, we find another theta k plus 1, which is the highest point of this q, and then we alternate. Okay, and we derive this lower bound using the Jensen inequality, and let me write down the expression for the lower bound, and then we will derive the E step. Actually, let me write down the E step and M step. That means that will make the things clear. Well, Z and Q are same, so I can write it this way. For a particular value of theta, which we call theta k, okay, and then in the M step, the highest point. Now Q is fixed. Let me call it QK. I could have, okay, fixing it at QK, and I make the argmax with respect to theta. Note that this is not theta k. Now theta can change. Okay, and this I call as my theta k plus 1. And this is my updated theta. Okay, and I alternate between these two steps. Now let me derive. I have already got the expression for Lz. So now let me try to solve this step. Then I'll solve the M step. Okay. Okay, so we got the expression for Q. Let me write down the expression for Q. It is, sorry, the expression for L. we establish that this is a lower bound on log of px given theta, and this L is indeed a lower bound using Jensen inequality. We got this. Alright. So our E step, in our E step, we wanted to, keeping theta fixed at theta k, we wanted to maximize with respect to q this L. Wanted to maximize this. Okay, in other words, we know this is a lower bound, so it cannot exceed this quantity. Instead, at a particular theta k, I want to find which q is the topmost one. Another way of saying is that, so maximizing this L is equivalent to maximizing the gap, since it is lower bound again, it is equivalent to maximizing the gap between the original log likelihood and the additional lower bound. Okay, it's minimized. So let us get the expression for the gap. Is, remember the original log likelihood. If we write down the expression for the original log likelihood, it is sorry, excuse me. Since xi are IID, I can write down the original likelihood like this and subtract L from this to get the gap. So this is my original log likelihood that I want to maximize, but I could not since it is complex, and this is my L. Okay, so let me write down the expression for L. Guess this also. Okay, so let us copy this expression. Okay, so this is my gap and I want to minimize this gap. Note that the minimum, I want to minimize this gap. Okay, so let me do a little bit of algebraic manipulation. So this quantity, I just do it this way. Okay, minus this entire thing. So what I have done is that this likelihood, this quantity, I have multiplied by this quantity because this quantity is, I have multiplied by this quantity because this quantity is equal to 1. Because Q is a probability distribution on the random variable Z, and Z can take on a value C. So all possible values C can take is 1 to K. So if we add up all these probabilities q, you will basically adding up the entire distribution. So this is equal to 1. So I can always multiply this log of xi given theta by this quantity. Okay, I can always multiply that. Also note that this summation is on C, and the quantity before the summation, this part is actually independent of C. So this entire quantity basically what I can do is that this thing I can bring in here, because this is independent of C. It does not depend on C. So if we do that, this becomes, I'm not writing this part right now. So this becomes I equals 1 to n, C equals 1 to k. I couldn't bring in inside because this part is independent of C. Log of xi given theta into, actually let me write it this way, q zi equals c into log of xi given theta. Okay, into log of xi given theta. So let me see what I can do with this. So now let me write down the entire gap, expression for the entire gap. So gap equals this quantity q zi equals c log of xi given theta minus summation I equals 1 to n, summation c equals 1 to k, this quantity, the lower bound quantity, c log of p xi comma theta equals c given theta y, the entire thing is inside log q theta equals c. Okay, so this is, I have just copied this is the expression. All right, so I can write this as I equals 1n, c equals 1 to k, q comes out, q is common to both, log of, then I have log of xi given theta minus log of p xi zi equals c given theta by q theta equals c. So log of this by this, which is same as I equals 1 to n, c equals 1 to k, q zi equals c log of, I missed the p everywhere, okay, log of p xi given theta divided by log of a minus log b is log of a by b, p xi. zi equals c given theta. This entire thing. Okay, so this is the entire thing. All right. So now let us try to do the definition of the joint probability. So I can write this as Q zi equals c log of p xi given theta q zi equals c, and this is I can write this up. P xi given theta zeta equal to c comma theta into p of zeta equal to c given theta. Okay, this is by expanding this term from the definition, simple probability, rule of probability. P joint distribution of xi and x and z given theta is joint distribution of x given z and theta into z given theta. Okay, so you see that this quantity zi given c okay, so if we assume z and theta to be independent, this quantity and this quantity is the same. So this becomes I equals 1 to n, this becomes I equals 1 to n c equals 1 to k q zeta equals c log of q zeta equals c given divided by p zeta equal to c given theta. This term cancels out. Okay, this gives theta. Okay, so this is my gap. Okay, so now let's see. So now see if you, what is the KL divergence between two distributions P and Q. It is summation over all values of x over which P and Q is defined, P log of P by Q. This is the definition of KL divergence. So this quantity you see is nothing but so Q is one distribution and P zeta equal to c given theta is another distribution. So this quantity is nothing but KL divergence between Q zeta equals c and P zeta equals c given theta. This gap is nothing gap between the likelihood and the lower bound is nothing but the KL divergence between the variational distribution Q and another distribution of the Zi given theta. X is not there. Okay, Zi given theta. So this is the gap. So as you remember before, we tried to change Q at some particular theta such that this gap is the smallest. That means the Q or the lower bound is as high as possible. So if you want to minimize this, you know the smallest value KL divergence is always greater than or equal to 0. So the smallest value that KL divergence can take is equal to 0. Okay. So if we do argmax of the gap with respect to Q, sorry, argmean it will not be argmax. You want to minimize the gap. Argmean of the gap with respect to Q, the smallest value this can take is 0 because the gap is equal to KL divergence. The smallest value it can take is 0, which basically means actually nothing. But see, when is KL divergence 0? When P and Q are same, exactly same, identically same, then the KL divergence is 0. So which basically means at theta, the log likelihood distribution and the variational distribution Q, they are one and the same, they match, they touch. That means it is no longer a lower bound, it is a lower bound, but it is a exact lower bound. The values are equal at theta, not at other points. Other point it is less, right? So that's what when you get. So basically what we get is, to minimize the gap, choose Q. The minimum gap is 0. The minimum gap corresponds to 0. That is when they touch Q and this. And the minimum gap becomes 0 when the KL divergence is the gap. So basically this gap is the KL divergence. And it can be made equal to 0 as the lowest value. And that's what we get the best Q. And when it equal to 0, the Q distribution is nothing but equal to this distribution Pzi equal to C given theta at that particular theta. So choose Q as Qzi equal to C is P. So choose Q as nothing but the conditional distribution of the latent variable Z given theta. That's your variational distribution. This will imply KL divergence to be equal to 0. This will imply the KL divergence to be equal to 0. So it is at this point when we get the highest Q. So let us summarize the Q step, E step. So in E step, so you remember in E step you fix theta k. So and we said that we have to maximize argmax with respect to Q, or rather I have already defined what the gap is, so I can as well write argmean with respect to Q gap, and that will imply that in the Q step you get your Q as, so basically set your Q to be this distribution, the conditional distribution of the latent variable given theta. Now think what is this in this Gaussian distribution. So if you think of Zi, that is C, taking a value either cluster 1 or cluster 2. So C is 1, 2 or 3 depending on which cluster it is. And Pzi equal to C given theta, basically means what is the probability a point xi belongs to cluster 1. Okay, and this you can easily compute for a given value of theta. So here you fix theta to be theta k. For a given value of theta you can do this. And this is your qk. For a given value of theta you can do this. So assuming some mean and variance of the Gaussian components and some mixer weights, you can easily find pzi equal to c given theta. That is your latent variable. Latent variable here is the class membership. That is your distribution. And your variational distribution is nothing but this latent variable distribution at a particular choice of mu, sigma and pi, the theta values, theta k values. Okay, so this is your E step where you get your Q. And next you go to the M step. M step, you remember what you do is that you now go to the highest point of that function. So first you find a good Q, then go to the highest point of that Q. So argmax with respect to theta, Qk Zi equals to C. But Qk I already know is this from my step. So it is basically argmax P Zi equal to C given my choice of theta k, and this will give my updated value of theta. This will give my updated value of theta. Okay, and here also you can see in the Gaussian distribution what it basically means. If you fix theta, that is some mu sigma, and you know that Zi equals to you know the probability of belonging to cluster 1. So what theta k plus 1 means, if you, the mean of theta k plus 1 is the mu 1 sigma 1. That is nothing but a maximum likelihood estimate of the Gaussian, which is just the data estimate. So basically mu 1 sigma 1 are the theta 1 in this case, for z1 equal to 1. That is nothing but the maximum likelihood, because see, this is just a Gaussian for the GMM case. Gaussian for cluster 1 or cluster C. So your theta you can easily estimate that if this is by this MLE estimate, you know that you can actually derive also. I actually leave it to an exercise. If you choose the exponential Gaussian form, take the partial derivative of this probability, because you know the form of this probability. This is a Gaussian. You take the partial derivative with respect to mu sigma, you get the theta. It turns out to be the GMM expression that we talked about earlier. So these are the two simple steps of the EM algorithm. Two simple steps of the EM algorithm. If you repeatedly do this till you converge to a constant likelihood value, the original likelihood, data likelihood value, Px given theta, then you stop. Okay, so this is my derivation, and I think have I given you the proof of the monotonicity of this thing? Let me quickly do that. Let me give you the proof of the monotonicity. Okay, so this is log of Px given theta. Suppose we start at some theta k. In the E step, what we will do, I draw a better picture. Right? So this is log of px given theta, and this is q. So this is my theta k, and this is kind of the best q that I am getting. You know that best q, it will touch at that point, KL divergence will be 0, and it is touching in this point, and this is my q z theta. I can call it q star, in some sense it is the best. This I do in my E step, and as I have told you, in the M step I fix q star. So in the E step I fix theta, find q star. In the M step I fix q star, find theta k plus 1, which is the highest point of this q star, theta k plus 1. Now see, now I tell that every iteration of this EMI, one E step plus one M step, will always lead to a new theta k plus 1, which has a higher likelihood, which is a higher point in this original function. Why? Because see, this is this red thing, this is q thing, is a lower bound on the original function, so it will stay below. So this point it touches, it stays below, and in the M state I am finding the maxima. So this point is above this point, since I am finding this is the maxima of this curve, and this is touching this curve here, this is the maxima of this curve. So this point is above this point, the like in along the y axis it is above. And since q is anyway lower bound, this will lie below the original curve. So this point at theta k plus 1 will be above this. So I can say now, combining these two, this point is above this point. So at every step, of E followed by M, the log likelihood value increases monotonically. Okay. So if that be so, after say 10 iteration or 100 iteration, I can always see it cannot get worse, it can only get better. So eventually, if not the global maxima, I will land up in some local maxima. So that's the proof of guarantee of convergence. Alright, so this is the generalized EM algorithm. I'm not doing it, so if you have gone through the steps of the E step and the M step, and if you understood this, this is actually called a method of variational optimization. You vary some lower bound and then optimize on it with respect to it. And two step, fix one, optimize other, and then fix that and optimize the variational function. So this is a general optimization technique used in many probabilistic algorithms, estimation algorithms, and I request you to follow the steps of this algorithm exactly for the Gaussian mixer model. The additional thing you need to do, the E step is easy, assuming the Gaussian mixer model. In the M step, the argmax with respect to theta, you have to take partial derivative of pzi equal to c given theta. You know that function, it is known for Gaussian closed form expression. You have to take a derivative of that with respect to mu, sigma and pi, and set that to be equal to 0. And if you do that and you get the expression for mu star, sigma star, mu, or rather mu k plus 1, sigma k plus 1, pi k plus 1, you will see they are exactly the same as the expression we derived earlier from our considerations. Okay, so I request you to do that. Otherwise, this is the end of the EM algorithm. There are many modern techniques which improves upon this, but I am not covering them. Thank you.